All right, so welcome back. We got a new experiment here. I'm at Rose State College, and this is called an air track, similar to how an air hockey table works, right? How's an air hockey table work? You got an air pump, right? And it's pushing air through little tiny needle-like holes. All right. Well, what does that actually do for us here? It creates a frictionless surface. All right, a frictionless surface. Right now we have this setup where this cart right here, this red cart, is on a string tied to a pulley to a 0.1 Newton weight over here, which is about 10 grams. 10 grams. And is that cart moving? It's not moving at all, is it? So what we're going to do is we're going to turn this thing on. All right. You can, if you'd like, you can time it at your house. I'm not going to time anything here. This is just for aesthetics, just to see a visual difference. What we're going to do is we're going to find out what happens when we release this after we turn the air cart on. Then we're going to do it again with a heavier weight, a 50-gram weight versus a 0.1 Newton weight. Okay? Oh, sorry, a 50-gram mass versus a 0.1 Newton weight. All right, so here we go. I won't be able to say anything while this pump is on, so just watch and learn. All right. Pretty slow, pretty slow. Let's do it one more time, just so you see. Then I'll put the 50-gram on. We'll do it 2 times. Note again, friction has set in. The cart is not moving. I'll just simply let this thing go, and let's see what happens. All right, that's enough of that one. Let's do the 50-gram. Okay. Still doesn't move. The friction here between the cart and the track is greater than that 50-gram mass. Okay? It's greater than that 50-gram mass. Just to note, we're calling this a 0.1 Newton weight. All right? That's just because it's imprinted on here. You can see really tiny. I'm not going to bring it close to the camera, but that's what it says. We just call this a 50-gram mass. They both have weight, all right? They both have mass. We're just, that's just the way it's imprinted on the object itself. All right, so here we go. Turning this on. 50 grams. Pretty big difference there. Pretty big difference. Try that one more time. Try it one more time. And we'll talk about what's going on. All right. So what exactly was happening there? All right. Cart's mass never changed. The cart's mass never changed once. What we changed was the mass, or the weight, hanging off the side here. All right. The air track experiment we just did. So what was going on there? I kind of gave a brief explanation of what was going on, but let's go into it a little bit more in depth. Okay, so I kind of drew up a diagram here. The air cart being pulled by a string, on the other end, a mass. Okay, M for a mass there, on the other end of this pulley. Okay, so explanation of air track demonstration. We have force is equal to mass times acceleration. So on one end, this has a particular mass. We'll call it the mass of the cart, M sub c, okay? Mass of the cart. it doesn't change between the two experiments. It does not change. But we do change this. We do change the mass that is pulling this cart down. Okay? We do change that. So when we do that, first of all, this mass of the cart is being accelerated by this string. Okay? It has this tension in it. It has a tension. So the cart is being accelerated by this string. Okay? It has this tension in it. It has a tension. So the cart, mass of the cart, and its acceleration is equal to the tension in this, that kind of looks like a time. It is equal to the tension in the string. Okay? The tension in the string. Okay? Well, the tension in the string over here on the other side of the pulley is just above this mass that's pulling it down. Okay? It's just above the mass that's pulling it down. So we're going to say that the tension in the string on the left side of the pulley is equal to the tension in the string on the right side of the pulley. Okay? So, and this is the mass of the cart and its acceleration. So, what makes the tension in the string? Right? It's the mass of the object, here the mass, that we used to drop this thing down, right? The mass, what we're going to call that, mass of the cylinder, or block, I guess we'll call it the mass of the block, times its acceleration. What was its acceleration? Gravity. Gravity, very good. Gravity is equal to the tension in the string. Okay? So, mass of the block times gravity is equal to the tension in the string. That was giving tension in the string. Okay? So, let's do away with all these string tension parts here, because this is equal to that, that's equal to that, and then that's equal to that. Okay? So we can do away with all these tension pieces here and just say that the mass of the cart and its acceleration is equal to the mass of the block times g. Okay? The mass of the cart times its acceleration is equal to the mass of the block times g. Okay? And they were both going in the same direction too. Okay? Well, sorry, not exactly. This is going down. This is going to the right. Had it been strong enough, it would have gone over the pulley and subsequently going in the same direction. But we didn't do that, thankfully. So, G never changed between the two experiments. We had mass of the block. We're going to change what we use mass of the block, and we're going to say mass 1 and mass 2. Okay? But mass of the cart stayed the same. Okay? We're going to call acceleration differently also. This is acceleration 1, this time with block 1. Mass of block 1 times gravity. And gravity never changed. Okay? Gravity never changed. Okay, so what did change? What did change is the mass over here. So mass of the cart never changed and gravity never changed. All right? So this has a particular force, right? Just like I said earlier. This has a force. Force 1 is equal to mass of block 1 times gravity. Okay? Force 1. So then we had to incorporate a new mass, which was 5 times the first mass. Okay? 5 times the first mass. So if we were to write the new one using the notation of mass 1, we would say 5 times m1. Okay? 5 times m1. So the other one, this would be force 1. This would be force 2. mass of the cart times acceleration 2 is equal to 5 times m1 times g, which is m2 times g. Okay? All three of these are the same. Don't be too confused. M2 is just 5 times M1, just like we said over here. Okay? It's just the same. All right? No need to worry about that. Okay, so now, how can we find out what our acceleration was? Okay? How can we find out what our acceleration was? For force 1, for acceleration 1, we'll rewrite it over here. We will say mCA1 is equal to m1 times g, okay? To find out the acceleration, well, mass of the cart is multiplying by the acceleration. How do you get it away? Well, you divide it away, okay? You divide it away. Mass of the cart, okay? Rewrite what you have. A1 is equal to m1 times g divided by mass of the cart, okay? m1 times g divided by the mass of the cart. All right, and so for the second one, I think we can already see how much more the acceleration was. Is equal to, dividing out mc again, dividing out mc, mass of the cart, we have 5 times m1 times g divided by mc, okay? And we don't even need numbers. We don't even need numbers to do this, okay? So that is the accelerations of the two, all right? And subsequently, the acceleration for the second block was about 5 times m1. And subsequently, the acceleration was 5 times the first acceleration. All right, thank you very much, and look forward to the next video. You have a good day.